Hi everyone, this is my lab number 5 and I use the following slinky model. This lab focuses on understanding the motion of a falling slinky. Our main goal is to predict what happens to the slinky as it falls, especially examining whether the bottom stays still for a period of time. We use two main tools, Tracker, which lets us analyze real recorded motion, and GlowScript, where we simulate ideal motion with physics. The question guiding the lab is whether the bottom of the slinky remains stationary in the model and the real observation. The results show that although there are small fluctuations, the bottom essentially stays still until the top collapses. Before looking at the data, it's important to understand the physical forces involved. So for the fundamental principles, we used Newton's second law, which tells us that an object's change in momentum depends on the net force acting on it. Drag force. Drag force is important because the slinky moves through air, creating resistance. Gravitational/slinky force. The slinky force itself is basically tension. This opposes gravity and plays a key role in why the bottom can stay still for a moment. These principles together help explain the slinky's behavior. So this is the observed motion. Here's the video model that I put into Tracker. So as we can see, the top of the slinky falls, but the bottom appears motionless. And this is what we're trying to understand and compare with our computational model. So this is my data from Tracker. For the computational model, the initial conditions I input were the mass, initial position, velocity, and the drag coefficient. All these values allow the model to approximate the real behavior, and the drag proportionality constant helps account for air resistance. So as you can see, I put for the mass 0.218, initial position negative 1.632 e to the negative 3, comma 2.725 e to the negative 4, and 0. Initial velocity was 0, and the drag proportionality constant was 75. The first while loop represents the time before the bottom begins to move. This lasts about 5.5333 seconds in the model. During this period, only gravity and tension are acting. The velocity and position update formulas compute the slinky's motion step by step. This part of the simulation aims to reproduce the stationary bottom. The second loop covers the moment when the bottom finally moves and the slinky reaches the ground, around 8.1333 seconds. Here, drag is added as a force to make the model more realistic. Again, velocity and position are updated using the forces in real time. This loop helps model the final part of the motion accurately. So for the results, this compares the model prediction with what we observed experimentally. The key result is the bottom remains stationary for most of the fall in both the real model and the simulation. Any small fluctuations likely come from measurement noise or physical imperfections. Overall, the model is a good representation of the real slinky behavior. So for possible sources of error, some possible sources of error include imperfect tracking from the software, the drag coefficient may not be perfectly accurate, and the slinky itself may not behave as a perfect spring, and the spring constant could vary. Small differences in the initial condition could also affect the accuracy. For further questions, I asked, what if we put a large weight at the bottom? Would it remain stationary? And why does the bottom of the slinky remain stationary? So for the first question, my answer was, it depends. As long as we have a slinky that is either long enough or has a large enough spring constant so that tension is equal to gravitational force, the weight will remain stationary until the top of the spring reaches it. And for the second question, the forces in the y direction cancel out. Although the gravitational forces act downward, the slinky acts as a big spring and counteracts the force with a tension force of equal and opposite magnitude. Thank you for listening to my presentation, and I hope you all have a great day.